When you think physics, the study of motion, you might picture things like pendulums, rockets, and planetary motion. But today, we're going to be talking about the physics behind music, which might just have a lot more to do with motion than you think. The key behind understanding the physics of music is the idea that sound is a wave. Just like waves travel through the ocean, sound travels as a wave through the air. Now there are two different types of waves, transverse and longitudinal. In a transverse wave, particles move perpendicularly to the direction of travel of the wave. In this example, the wave moves horizontally, but each particle is moving up and down. In a longitudinal wave, on the other hand, particles move parallel to the direction of travel of the wave. When I hit the pool balls, each one moves horizontally, along with the overall wave. This is the way sound travels through air, with each air particle moving in the same direction. When you hear a pitch, your brain is actually recognizing a series of waves, and the property of these waves is the key to what makes things sound different. Let's have a look at some of these waves. While sound is a longitudinal wave, it's easiest to model sound using a transverse wave. On this wave, you'll find high points, crests, and low points, troughs. Two terms that are important here are wavelength and frequency. Wavelength is essentially one cycle of the wave. This is the distance between two crests or two troughs. In this case, the wavelength is about 7 centimeters, or 0.07 meters. Frequency, on the other hand, is defined as the number of wave cycles per second. Overall, this is the basis of a sound wave. This brings us to the fundamental formula V equals F lambda. In this equation, V is the velocity of the wave, which in our case is going to be the speed of sound. F is the frequency, which is measured in hertz. Hertz essentially means per second. And lambda is the variable that we use to describe wavelength. The speed of sound is relatively constant, and we see that there's an inverse relationship between wavelength and frequency. As one goes up, the other goes down. Now let's tie this back in with music. Pitch is essentially how high or low a note is, and is directly related to frequency. This means that a high frequency note is going to be a high sound, while a low frequency note is a low sound. Given the formula, we can figure out that short wavelengths correspond with the high notes, and longer wavelengths correspond with the lower notes. This makes intuitive sense. We all know that smaller instruments make higher pitch sounds, while lower instruments produce lower sounds. A piano provides a good example. You'll notice on the piano that the shortest string corresponds to the highest note, and the strings get longer as the notes get lower, with the longest string being for the lowest note. This is because of the relationship between wavelength and frequency. As the wavelength increases, the pitch decreases. This idea is common across all instruments. On the flute, the note gets lower as I close the holes by putting down my fingers. As the instrument effectively gets longer, the wavelength increases and the notes get lower. The same is true for the saxophone. You'll find that the lowest note is all the holes closed, while the highest note is all holes open. The idea of tuning on the saxophone takes advantage of this property of wavelength. When I push the mouthpiece in, it shortens the tube. This makes the note sharp, meaning it's too high. When I pull out the mouthpiece, on the other hand, it lengthens the tube. This makes the note flat, meaning it's too low. So what's actually going on in these instruments? The saxophone looks awfully complicated, but the physics behind it are actually quite simple. It produces sound when air is blown past the reed, the wooden part on the mouthpiece. The reed vibrates, oscillating back and forth like a flag in the wind. The wave formed inside the instrument involves a closed end and an open end. This means that the wave will look like this, 1/4 of a wavelength. The flute produces sounds when the player blows a stream of air across the open hole, where it splits and oscillates, creating sound just like blowing air over a bottle. The flute actually has two open holes, one at the head joint and one at the bottom. This means that the wave will look like this, half a wavelength. The flute is also really good at demonstrating harmonics, which is the key to what makes music sound so good. Now, watch what I can do even if I hold the same fingers down on the flute. Now, how was I able to do that? Well, the secret is that there's much more to the flute and much more to the story than that first wave we first looked at. Let's go back to that first basic wave we looked at, formed inside the flute, with the two open holes. Waves will only resonate in this instrument if there's an open end on either side. But that's not the only wave that meets those criteria. If we blow differently, we can also form this wave. This wave has a shorter wavelength, even though the overall length of the tube is the same. The shorter wavelength means that the frequency is going to be higher, which means that the note is also going to be higher. As the wavelengths decrease, the notes keep getting higher. And this trend continues as long as all the waves have open ends on either side. Let's do some calculations to prove what's going on here. The first note I played was a C, which is 262 Hz. Now the next possible wave formation is exactly half the wavelength, which will be double the frequency. If we double the original frequency, we get a result of 524 Hz. We find that this was the second note that I played in the series. Continuing on, we see that the next wave has exactly 1/3 the original wavelength, so 3 times the frequency. Doing the calculation, we find that this gives us a frequency of 786 Hz. This, as it turns out, was the third note that I played. This same pattern also goes for the fourth and the fifth notes that I played. If we continue the calculations, we find even more notes. This series of notes is called the Harmonic Series. This is our last piece of the puzzle, and it's the key to what makes music sound so good. The distance between two notes is called an interval. So let's take a look at some of the intervals in this series. Going from first to second, we double the frequency. From second to third, there's a ratio of 3:2. From third to fourth, that ratio is 4:3, and from fourth to fifth, 5:4. You may have noticed that these are nice, simple fractions. Now, let's apply this back to music using a piano. Let's start with A, with a nice even frequency of 440. Let's look at our first interval, a ratio of 2:1. If we multiply this by our fundamental frequency, we get 880 Hz. This corresponds to the note A. Let's hear that. You might notice that these notes sound about the same. That's because they basically are. They have the same name, and they're located in the same area of the keyboard. This interval is called an octave. You can hear octa in there, meaning 8, as in octopus or octagon. This means that the upper note is the 8th note of the scale. Let's keep going. Our next interval is a ratio of 3:2. This gives us a frequency of 660 Hz, which is the note E. Let's give that a listen. That's a really nice sound. This is called a perfect fifth, because the upper note is the 5th note in the scale. Moving on, we find that the next ratio is 4:3. This gives us a frequency of 587 Hz, which is the note D. Let's listen to that one. Also really nice sounding. This interval is called the perfect fourth, because the upper note is the 4th note of the scale. The final ratio that we're going to be looking at is that with a ratio of 5:4. This is going to give us a frequency of 550 Hz, which is what we call a C sharp. Let's have a listen. just beautiful. This interval is called the major third, having its upper note as the third note of the scale. What we've stumbled upon here is just amazing. These simplest fractions produce such beautiful sounds, and more complicated fractions often sound messier. This is what a 16 to 15 ratio sounds like. Not quite as pretty. By delving into the physics behind music, from the wavelengths to the frequencies, all the way to these ratios that we've talked about, we've discovered why music sounds so good to our ears. As with everything in life, the greatest beauty comes in the smallest packages and in the details that too often go unnoticed. Under every question is an infinite world of knowledge waiting to be discovered and understood. Thank you.